We look at this final problem. This one would be the trickiest of the three problems that I've uploaded for you guys. And that's because I have two frictional sections, which just means that I have to account for work twice at one point during the problem. If you understand that any time we have this outside force, again, usually friction, that's affecting this system and the energy within it, I just have to account for that by incorporating the work into my calculation. Granted, at part B, or at location B, it's a little bit trickier, but I will show you how, in my opinion, you can simplify the problem. So let's start first by looking at what would the velocity of this object be at point A. Okay, just like every other problem, we need to choose two locations. So again, I think the starting point is a good one, and A is a good one. Now again, I generally like the starting point because there's usually enough information. However, sometimes there's not. Sometimes the information where you have enough of those pieces to solve would be at point A, and then you might have to work backwards. But for right now, we have all the starting information, and I'm looking for the velocity at point A, so it's pretty straightforward to use my starting point and location A. Now I have some friction, I have some outside forces that are affecting what's going on in this problem between the starting point and location A, so I have to account for the fact that work occurs. So I will use the entire equation with the work incorporated on the starting side. I will then cancel out, well, I have no GPE and no EPE for the start, so all I'm left with is the kinetic energy to begin with, plus whatever work occurs during this section, and that must equal whatever I'm left over with at point A, which only happens to be kinetic energy, as there's no height and there's no spring compression at point A. So what I'm left with is 1 half mv squared at the beginning, plus whatever force of friction acts on that object over whatever distance, times the cosine of the angle between them, must equal the kinetic energy I have at point A. So if I plug in everything that's known, I know the mass is 30 and the velocity is 8. For the force, I know that the force of friction is 30 newtons. It acts over 8 meters, and because friction opposes the motion, that angle between those two is 180 degrees. Well, I know this entire side, so I can set it equal to the kinetic energy at location A, which is 1 half the mass, times this unknown velocity. What I can then do is plug it into my calculator, and if I solve correctly, I can find that that object is traveling at 6.93 meters per second at location A. You'll find that the total mechanical energy it had at A is less than the total mechanical energy it started with. Why? Because this friction performed work and took some of that energy away. It's now still in the universe, but it's now heat, sound, some other form that is no longer usable by that moving object. All right, so now for the super fun part. How far is this object after it passes over this frictional section, after it travels through location A, and after it travels on to this second frictional section? How far is it going to slide before it actually comes to rest? So what is the stopping distance on that second frictional surface? Well, just like every other problem, we need two locations. You could certainly use A and B, but you know what? I've already calculated the energies associated with the starting point, so I'm just going to stick with that. So what I'll do is I notice my locations are my starting location and point B, and not only do I have work, but I have work twice between my starting and B. I have once before A and then once as I travel on to that section located by B. So how do I account for that? Well, I quite simply write out my equation again, potential, kinetic, and potential on both sides, but I just quite simply write work at A plus work at B. So when I cross out everything, because everything's just on the ground, I realize that the kinetic energy that I start with here, plus the work that's being performed by A, plus all the work that's being performed by B, that must equal 0. Wait, why 0? Well, the object, when it comes to rest at location B, has no height, no velocity, and no spring compression. So it seems weird, but I'm just showing that this work occurs at two different locations. I then plug in everything I have. 1 half mv squared, which is the kinetic at the start. Now the work at A is just the force at A, which in this case is 30, so I would not use this. I use the 30 for location A. I use the 8 for location B in terms of its displacement. For B, I'll use the 40. For B, I don't know what the displacement is. But if I plug everything in, I know the mass and the velocity to start with. I know the force and the displacement at A. I know the angle between them is 180 degrees because friction always opposes the motion of an object. At B, I know the force of friction is 40. I don't know how far it's going to slide on, but I do know that these act 180 degrees, as I mentioned before, because it's friction. And I know that at the very end of the day, because I'm on level ground and I'm at rest and there's no springs, that energy must be gone. So, how far will it slide onto that sectional friction, second frictional section, in order to ensure that all that energy by the end becomes heat and sound and is no longer in that ball? Well, if I've done this correctly, you should find that it must travel a total displacement of 18 meters.